Integrating differential equations and then modelling using integration is the culmination of all the concepts that you may have come across in integration and indeed differentiation as well. So as such, as we go through these examples here, we're going to be focusing more on what is solely involved in integrating the differential equations, that is the rearranging in these specific cases, and then when the modelling, how to make those specific equations, more so than focusing on the actual methods of integration itself. So if you go through practice integrating differential equations questions, you may come across parts which require integration by substitution or reverse chain rule or integration by parts. For help on those, I would suggest going to those videos specifically in and of themselves. Of course, we are going to be touching upon those kind of integration methods here anyway, but again, they are not going to be the prime focus. What we're going to be looking at then is the question such as this. We have given that y equals 8 and x equals 1, solve dy over dx equals 9x plus 6 in brackets times by y to the third, all divided by x, giving it in the form of y squared equals gx, basically just making y squared the subject. Now here, when we say solve, that means we're trying to get to the form, well, in this case, we're trying to get to y squared, but if it hadn't specified, then we'd be trying to get to the point where it's y equals, and trying to make y the subject outside of a differential back into whatever regular equation of a curve this would have been. Now, because we're starting in the differential, we would think to integrate, but like when we have implicit differentiation in the differentiation topics, we have here a mixture of x and y. So we're going to have to do some rewriting first before we can integrate, because we can only integrate when there's a single letter on the side of it's like d that letter. So we're going to integrate x when we have dx, integrate y when we have dy. So to start off with, as we need to move the y onto the side of the dy. Right now it's times up the top of the fraction, so we would divide it across. It would become 1 over y to the power of a third dy, and then to get the dx on the same side as the rest, we would times that up. This we would then just write as our 9x plus 6 over x dx, therefore. Before we get into the actual integration, we may wish to rewrite this a little bit further to make it more convenient for integration. So 1 over y to the third is the same as y to the minus a third, and still dy. And then this fraction here, 9x divided by x, we could say it's just going to be 9. And then this will still be like 6 of x, or 6x to the minus 1 dx. Now that we have them in power form, now we'll probably want to do that integration. Because when we're integrating, we want to add 1 to the power, divide by the new power, so we want to be able to tell exactly what the current power is. So here, to add 1 to minus a third would become 2/3, so y to the 2/3. Then to divide by this new power would just end up being 3 over 2. So 3 over 2, y to the 2/3, equals 9 will become 9x. 6x to the minus 1 is going to become 6 ln x. And then we just have to put a plus c. You don't need to put a plus c on both sides, because you could then just imagine you've minus this constant over here and they would amalgamate to some other unknown. So because we haven't got a specific value yet, it's fine to just leave it as this nebulous thing on one side. We do need to work out what it is though, and how we're going to do that is by plugging in the x and the y. So if we were to minus these two terms over here to just get the c on its own, you would have, so 3 over 2 lots of 8, to the 2/3, minus 9 lots of 1, minus 6 lots of ln1, and altogether that will get you c, and you get that it's a value of minus 3. Therefore, if we were to try to now just get the y squared on its own, from currently having 3 over 2 y to the 2/3, first of all, we would be dividing by the 3 over 2, or in other words, timesing the right-hand side by 2/3. 2/3 of 9 is going to be 6, so 6x. 2/3 of 6 is 4, so plus 4 ln x. And then 2/3 of minus 3 is going to be minus 2. To then go from your y to 2/3, so just y squared. you would then need to cube. So this whole expression just becomes cubed. And to be clear, you don't have to expand this now. I mean, you could if you wanted, but so long as the y squared is on its own, you're fine. At most, I'd say a rewriting you may want to go so far as doing is maybe just simplifying this slightly, take out a common factor of 2, just so long as you make sure it still has the cube next to it. So in other words, that's going to be 8. And then if we take out that factor of 2 here, that would leave us with 3x plus 2 ln x minus 1. Then this again, still all being cubed. Okay? So again, the priority here, first of all, just get the y's on the side of the dy, get the dx on the side of the x, then integrate both sides as you usually would, plug in an x and y if you have them to work out c, and then rearrange into whatever form they're looking for. Again, I already alluded to before, this can lead to the use of any of our integration methods, so by parts, substitution, and so forth. It can also rely on us using, well, first of all, the natural logs, but also some trigonomic identities. So it's probably worthwhile that we just go over such a question like that as well. So here, given that y equals 0 at x equals pi over 3, solve 2 cot x dy dx equals 4 minus y squared in the form of sec squared x equals gy. So again, we're going to be trying to make sec squared the subject here. As you can see, we've already got our, even though they're not on the same side, multiple x's and y's here that we're going to have to be integrating. And because we're acknowledging we've got a trigonomic function here, our cot, which if you remember is 1 over tan, and our x is now going to be pi over 3. This is telling us already that for this question, we're going to want to make sure that our calculator is in the radian setting. In fact, actually, I should probably say at this point, this topic does only work in the radian setting. Obviously, that only makes a difference when we do have a trigonomic function in the question, such as this. But even if the question doesn't specify that your x is in terms of pi, we're still going to want to be making sure that if you have a sine, cos, or tan, or whatever, that you are in that radian setting. Once you've just made sure of that, you can now start off by moving the x's around, moving the y's around. The dy is always going to stay on the left because it's already in the numerator. You don't want your d expression to be in a denominator, so keep that over here. So the y has to move left. So that's going to become 1 over 4 minus y squared dy, and then you move the dx over here, as well as the 2 cot x. Now, to be clear when you move this over, because cot is 1 over tan, when you move that over, that's going to become tan x on the other side. But moving the 2 cot x over, that is not going to become 2 tan x. Imagine just moving them one at a time. If you move the cot x over first, as in 1 over cot x, 1 over tan, just becomes tan x again. But if you were to then move the 2 separately, that then just becomes a half. Okay, so this number here, this coefficient, is still going to be in a denominator here, even if you then brought the 1 over tan up, then brought the tan up to become a numerator here. This then just being connected to that dx. In this form, though, while we could integrate the right-hand side now, using a formula from the formula book as to what tan integrates to, this here would not be the best thing to try to integrate. We may actually want to split that up into partial fractions first. And in fact, a full question in a paper may have already prompted you to do that in like a part A to the question. So to just split this into partial fractions over here, the denominator, first of all, we need to work out, well, what can that be split up into? Because this is the difference of 2 squares, we can say that will be 2 plus y and 2 minus y. Therefore, this will equal a over the first bracket, your 2 plus y, plus b over the second bracket, the 2 minus y. Timesing up by both of those brackets, therefore, you're left with just 1 on the left-hand side, and then a is left being times by the 2 minus y, and the b is left being times by the 2 plus y. At this stage, you substitute in y values that would get rid of either of the brackets. So if we do y equals 2 first, 1 stays the same because it's not related to y. 2 minus 2 will become 0, so the a term disappears. So we're just left with 2 and 2, which is 4, 4b. Therefore, b is going to equal a quarter if you divide that 4 over. If we now do a similar thing with y is minus 2, again, 1 is unaffected. 2 minus minus 2, it's like 2 add 2, so you've got 4a, and then 2 minus 2 here will disappear, b goes away. Therefore, we can say that a is also 1/4. Therefore, this could be written as 1 over 4 lots of v2 plus y plus 1 over 4 lots of 2 minus y, all dy being integrated, and again this so far could have stayed the same, it's just the integral of a half tan x dx. To integrate these, because the 2 plus y, the phrase that contains the y, would essentially have a power of minus 1, that means that when you integrate it, it's going to go to a natural log. This 4 though stays in the denominator, it's still a quarter, so it becomes a quarter of the natural log of the 2 plus y. But then here, while this 2 would become a quarter of the natural log of 2 minus y, because when you integrate like this, you are meant to divide by the differential of the bracket of the ln. The differential with respect to y of 2 plus y is just 1, so divided by 1 makes no difference. But the differential of 2 minus y is minus 1, so we need to divide by minus 1, which turns that plus into a minus here. Then, on the right-hand side, using the formula book, you would find that tan integrates to the natural log of sec x, and then we'll have that plus c that we need to include for the moment. To work out what that c is going to be, like before, we'll just need to substitute in the y's and the x's that we know. On the left-hand side here, because they're the same logarithm, they're both natural logs, and they both have the same coefficient, we can use the rule where the logarithms subtracted from each other would be the same as just having the contents of this bracket here divided by the contents of this bracket in a single logarithm, and then we would be saying that equals a half of the natural log of 1 over cos of x, and that obviously equals plus c, but instead of our y's and our x's, we'll be having our zeros and pi over 3, so 2 plus 0, 2 minus 0, and pi over 3 here. To solve this, therefore, you would end up with c having to equal minus the natural log of the square root of 2. Now, it's possible your calculator is going to give this to you as a decimal instead, in which case, while you can use that, because you would inherently be rounding the decimal, that wouldn't be exactly correct, it would not be perfect. So, what you would find is on the left-hand side, if we were to do this manually instead, just to double check, is that what is essentially 2 over 2 is going to be the same as 1. The natural log of 1 is 0, so this entire left-hand side is 0. Therefore, c has to be whatever is needed to cancel out with this first term. Well, the cos of pi over 3 would be a half, so 1 over a half is 2. So this is currently a half ln 2. But then, just because of how logarithms work, we can bring the coefficient up inside as a power. So this would be natural log of 2 to the power of a half, which is also just the square root of 2. Therefore, to make this disappear, c must be minus, and then also that natural log of root 2. That's where we can derive this from if we need to, if the calculator is only giving it as a decimal. Either way then, if we are now trying to essentially get sec x to be the subject, we already have on the right-hand side that this would come together to be the natural log, and actually if we could bring in, again, this coefficient as a power, it becomes a 2 plus y to the power of a quarter over 2 minus y to the power of a quarter. If we were to now, well, if this is a minus already, the c, moving it over would make it positive, so add the natural log of root 2. This equals the natural log of sec to the half of x here, because again we'll bring the power in, the coefficient in as power. Right now, actually, because we have an addition here in terms of our logarithms, we could combine that further into an even bigger single logarithm, because with the addition rule, we're saying that's like timesing the contents of the bracket. So now actually we might as well just extend this fraction a little and just say that's times by the root of 2. Now both sides are single terms that are both natural logarithms. Therefore, you can basically just get rid of those logarithms, leaving you with just the contents of the brackets having to be equal to each other. So 2 plus y to the power of a quarter times by root 2 all over 2 minus y to the power of a quarter is the same as sec x to the power of a half. Well, how are we then going to turn sec x to the power of a half into sec squared as we want? Well, squaring this term would turn it into a singular sec x, because power of a half is like square root. And then how would you turn the regular sec into sec squared? Well, you would square again. So we are going to square, then square, which is the same as doing it to the power of 4. So our sec squared x, that would be all of these each time to the power of 4. Here, if it's already to the power of a quarter, and you're going to do that to the power of 4, that would cancel out to just be a power of 1. So you're just going to have your 2 plus y, and then root 2 squared would be 2, then squared again would be 4. So we've got 4 lots of the 2 plus y, and then on the bottom, that would now just become that 2 minus y, again, because the power of a quarter to the power of 4 would cancel out as a single power. This fraction, therefore, is your equation when the other side is made to be sec squared x. Again, that's just, again, another example of how we can be using our integrating of differential equations, but also just tying in some other concepts, some other part of integration, whether that's our trigonomic identities or partial fractions. As we move now into the modelling side of things, this is where we have our scenarios, either from a diagram or a written description that we need to create equations from. If you think about how we've done modelling with differentiation, we're now again going to be working with integrating differential equations, but it's more complex scenarios, as we'll now see. So, if say on the left here we had the rate of increase of n fish is dn over dt equals first bracket kt minus 1, close bracket, then the second bracket 5,000 minus n, close bracket, all over t, where t is the number of years since 2000 and k is positive. Show that n equals 5,000 minus at e to the power of minus kt. So, to begin with, because we're going from a differential expression, a dn over dt, to where it's just n on its own, this is telling us we're going to be integrating. But in order to integrate this, we're going to need to bring the n's on the same side as the dn and the dt on the same side as the t's. So we'll divide over this whole phrase here. We can't just move over the n on its own because it's within a bracket with its own contents. So move that entire bracket over. We'll have 1 over 5,000 minus n dn. That's going to equal, now on the other side, just the kt divided by t will just be k, and then that's minus 1 over t there, dt. Now that each letter is on the same side as its d term, we can just integrate both of those. This gets us on the left-hand side, therefore, what would be the natural log of 5,000 minus n, because it's essentially the entire denominator to the minus 1. However, as before, you need to divide by the differential of what's in the bracket. In this case, with respect to n, this would differentiate to minus 1. So divide by minus 1, sticks a minus in front. Then that will equal, with respect to t, k is going to become kt, and then minus 1 over t will become minus lnt, after which you need to add your c. Now at this stage, because we don't have yet any values for n or t with which to work out c, we're just going to have to keep working around it as an unknown and instead focus on making n the subject. To get n out of this bracket here, we're going to have to get rid of the natural log on this side, which means raising the right-hand side as e to a power of that. But first, we may just want to, imagine we're switching over the sides of the equal sign, basically make this a plus, make this a minus, make this a plus. C doesn't matter because, again, it's an unknown. We don't know whether it itself is a plus or a minus. It's kind of nebulous. You can make it a minus if you want, but it doesn't make a difference to the overall working. Now, yeah, we can do that and say that, okay, this would still be 5,000 minus n on the left, but now it's all e to the minus kt plus lnt plus c on the right-hand side. Now, what to do with this? Well, because they're added in the power, that's like saying that it's e to the minus kt times e to the lnt times e to the c. So when you times terms together, that adds powers. If we're trying to make n the subject, because now it's minus n, you want to add it over to the other side, but then we obviously don't want it now connected to all of these e terms, so we'll minus those back over. So n equals 5,000 minus, and again I'm going to just write that as e to the c first of all, times by e to the lnt times by e to the minus kt. Now, the reason I've written it that way is to keep it in the order that we're trying to show at the end. So this will be still 5,000 first, but then minus, so your e to the c doesn't change, e to the lnt, e, and then having an ln in the power cancels, leaving that just being t, hence how we've got t in the middle here, and then the e to the minus kt, that was always meant to be at the end in that form anyway. So we've now got it in this form. We're just saying, therefore, that a equals e to the power of c. Whatever c would have ended up being, we don't have to work it out like this. So now that we have this general equation, we've shown this, and again, a helpful thing about this style of question is even if you didn't get to work out what this is, we can then carry it forwards in the next part because it was to show that. So now that we have this equation, in 2001 there were 1,200 fish. In 2002 there were 1,800. Therefore find A and K. So we can now plug these values of n with a value of t that we can derive, because remember t is the number of years since 2000. So here, if when the population was 1,200, that'll equal 5,000 minus a that we don't know, but 2001 is 1 year after 2000, so t is 1, and then e to the minus k 1. So in other words, you've got 5,000 minus a e to the minus k, and then with the other one, 1,800 equals 5,000 minus a times 2, because it's 2 years afterwards, e to the minus k times 2. So in other words, 5,000 minus 2a e to the minus 2k. Now, what to do with these? Well, we can rearrange these to make the a and ek terms the subject, so add those over onto the left-hand side and minus the 1,200 or the 1,800 onto the right-hand side. Basically how we made n the subject above. So we'll end up with a e to the minus k equals 5,000 minus 1,200, which is just going to equal 3,800. And then 2a e to the minus 2k equals 5,000 minus 1,800, which will just equal 3,200. And yet, because we're probably going to be trying to compare these, what we can do is we can divide by a factor of 2 here to leave us with, again, a single a in front. So divide all of this by 2. We end up with the 3,200 instead being 1,600. So ae to the minus k equals 3,800, and ae to the minus 2k equals 1,600. Therefore, what we can now do is divide the expressions by each other. So ae to the minus k divided by ae to the minus 2k equals 3,800 divided by 1,600. Well, here the a is going to cancel with the a, hence why we divided. And then here, e to the minus k divided by e to the minus 2k, that's going to come back around to just be e to the single positive k, because at minus k minus minus 2k, and that will equal 19 over 8. Therefore, k equals the natural log of 19 over 8. Now that we have k, we can go about working out a just by substituting it back into any earlier bit. So what we can say is that a would equal the 3,800 divided by e to the minus, and again k we now know is ln 19 over 8. And if you just put that into your calculator, you would end up with a being 9,025. This, to clarify, is the end of the question. That is what we need to work out. But if you did then just want to write it out as a full equation just to check for yourself or to understand where everything goes, what we can say therefore is that n equals 5,000 minus 9,025 t e to the minus ln 19 over 8 t. That is the equation that is ultimately relating n and t throughout all of this question. Okay? So if we can see how in these past three examples we have been moving around our terms so that we can integrate them using various techniques, and then in this latest example how we can then use information from the rest of the scenario to find unknowns, to create an overall equation with the only unknowns being the variables. If we're good with that, let's just see how you might get along with an example of your own. If P0 is the initial population, solve in terms of P0, lambda and t, the expression dp over dt equals lambda p cos of lambda t. So to be clear, when we're saying we're solving this in this case, what we'll be doing is we're making p the subject. If P0 is then the initial population, think about what that means in the context of this expression, of this equation, how the initial population is going to potentially be different to the general population. And again, also think how you're potentially going to integrate this trigonomic function here after moving things around. And then also, once you've done this, you also have, given that lambda equals 2.5, find the time to the nearest minute, given that t is otherwise in days, that the population reaches 2 lots of P0. So again, there's no need to worry about lambda being 2.5 until the second half of the question. No one need to worry about what unit of time t is in. But when you get down here, yes, think, okay, how are you going to solve for t? And how are you going to turn a t that's in days into t to the nearest minutes? And what does it mean for the population to now be twice its initial? So again, considering all of this, just pause the video, have a go for yourself, play around with the equations, and then press play again when you're ready to compare. So if we are starting off by just, again, as per usual with these questions, bringing the p onto the same side as the dp, dt on the same side as t, I might just suggest moving the p alone over, so make it 1 over p dp here, and that leaves you with lambda cos lambda t dt here, both of which you can then integrate. While it would be fine if you had brought the lambda over with the p, we should see when we start with our integration that it actually may make things a little simpler if we keep it over here. So our 1 over p with respect to p is just going to integrate to the natural log of p, and that will then equal cos is going to integrate to sine. But also, when you have a coefficient to your variable in the trigonomic function like this, when you integrate, you have to divide by the differential of that bracket. So in this case, the differential of the bracket would just be lambda. So we'll divide by lambda. So by dividing by lambda, we get rid of that coefficient at the beginning. That's why it can just simplify things slightly to keep it over here, because now we're just left with sine of lambda t plus c, as before. Therefore, if we were just to try to make p the subject, we'll need to get it out of the bracket. We'll need to raise all of the right-hand side as e to a power, so e to the power of sine lambda t plus c. As before, if it's added in the power, that means we can essentially just think of it as two separate e terms with the individual powers just times together. Now we're not there yet because it still wants it in terms of p0 as well. We need to introduce a p0 somewhere. Well, if it's the initial population, that means that that is when time is 0. So if we were to try to make this an equation for the initial population, so now make it p0 on the left, you have e to the sine of lambda 0, then e to the c. It doesn't matter, therefore, that your whatever lambda is, because lambda times 0 is 0, sine 0 is 0. E to the power of 0 is 1. So p0 equals 1 times e to the c, therefore e to the c equals p0. Therefore, we can say, going back to the previous expression, that the general p here equals, and just bring this in front as a coefficient, p0 e to the sine lambda t. In general, with these kind of equations, especially when you're going to have an exponential in there, you'll find that any coefficient of the e term tends to be the initial value, because then t will be in the power, and when t is 0, that just makes the whole e term usually turn to 1. So left-hand side just equals coefficient here when t is 0. As a general rule of thumb, coefficient of the exponential tends to end up being the initial of whatever this thing is. But then once you've had that, so now we can start introducing the idea that lambda is 2.5, and we're now trying to find the time when the population on the left is now double the initial population that we had on the right. So 2 lots of p0 equals p0 e to the power of sine lambda t. Divide through by your common factor of p0, that just leaves you with 2 equals e to the sine lambda t. Therefore, to start trying to get t on its own, we're going to need to bring this whole power down. How we're going to do that is going to take natural logs. So therefore, the natural log of 2 of the left-hand side will equal, e goes away, so we're just going to say it's sine of lambda t. So to now just try to get the t on its own, we would take the inverse sine. So lambda t on its own, and again actually we can replace lambda, can't we? So we can just say that's 2.5t equals the sine inverse of your natural log of 2. And then just to get the t on its own, we would now divide by the 2.5. Put this whole expression into your calculator, and you are going to get 0.306 days. Remember, it's in days. Also remember, when you've done that, as I said before, this topic only works in radians. So you want to make sure that when you did your inverse sine here, that you were still in the radians function. Now we just come to that final little step of turning these days into something to the nearest minutes. So to turn days into minutes, you can first of all turn it into hours by timesing it by 24. And to turn hours into minutes, you times by a further 60. So this gets you to the nearest whole number, to the nearest minute, 441. Okay. If we're happy with that, again, we see how we did each stage, use information available to create equations, and how we then use those equations to find other unknowns. Let's just wrap up with one further example. So, a spherical mint of radius 5 mm is placed in the mouth and sucked. 4 minutes later, the radius of the mint is 3 mm. In a simple model, the rate of decrease of the radius of the mint is inversely proportional to the square of the radius. Using this model and all the information given, find an equation linking the radius of the mint and the time, where we should define the variables that we use. Then hence find the total time taken for the mint to completely disappear. Give your answers in minutes and seconds to the nearest second, and then suggest a limitation of that model. This, of course, we're now just going to take step by step. So to start off with, when it says defining your variables, that means we just need to specify that r equals the radius in millimeters and that t equals time, and we'll say in minutes. because the unit we have been given thus far is 4 minutes there. Again, just because the question hasn't actually given us any equation, this is why we have to specify for ourselves. And also in case, for whatever reason, you could use other letters as well, like you could use X and Y or something. And just in case you had done that, you just need to make it explicitly clear what each letter is representing, right? Now, like when we were doing the modelling of differentiation, we need to create these expressions for ourselves. So like when we had rates of change, we've got a mention of rates here. So the rate of decrease of the radius is inversely proportional to the square of the radius. So the rate of decrease of the radius, so it's rate, so it has to be dt on the bottom, and it's relating to the radius, so dr on the top. It's a decrease, so we're going to have a minus. And then when it's inversely proportional, we're saying that that's going to be some constant divided by whatever the other thing is. So in this case, the square of the radius, k over r squared. If it had been directly proportional, it would have been k times r squared. But now that we have this equation, we can start trying to integrate to try to get an equation involving r and t. So we'll need to bring the r onto the same side as the dr, so this will just times up here to be r squared dr. Then on the other side we'll have minus k dt, both of which we can now just integrate. So r squared is going to become a third r cubed, and that will equal minus kt plus c. Now, how are we going to work out our k and our c? Because we need to specify what those are to get a full equation. Well, we'll now use the first couple of sentences. The idea that when it's first placed in the mouth, when time is 0 presumably, the radius is 5. So we'll say that a third of 5 cubed equals minus k times 0 plus c. Therefore, obviously the times 0 here is going to make the k term disappear. So c is simply going to be a third of 5 cubed, which is going to end up being 125 over 3. That's not going to simplify any further. But now that we have this, we can now plug that back in to solve for k using the other sentence. So we can say that a third of 3 cubed equals minus k times 4 plus 125 over 3. So if you were to do a third of 3 cubed, which is just going to be 9, and minus the 125 over 3, and then divide by the minus 4, you would end up with k equaling 49 over 6. Therefore, if we now just put that back into our previous equation, we have a third of r cubed equals minus 49 over 6 t plus 125 over 3, which if you just wanted to make r on its own the subject, what we could say is if you divided by a third, you would just have minus 49 over 2 t plus 125, and then you'd need to cube root that, or if you want, just like to the power of third. With this equation now in hand relating the radius to the time, we can now find out, well, what would be the total time taken for the mint to dissolve, giving it in minutes and seconds. Because we're going to be solving for t, we might as well actually just go from this version of the equation here, because otherwise we'll just have to, cube the thing back. So because it's going to have completely dissolved, that means the radius is now 0. So you're going to have a third of 0 cubed equals the minus 49 over 6 t plus 125 over 3. Obviously, this being 0 here makes that entire left-hand side equal 0. So we can just add this term over to get 49 over 6 t equals the 125 over 3. Therefore, t is going to equal 125 over 3 divided by 49 over 6. Which would get you, remember this is in minutes because that's what we framed t as before, 250 over 49 minutes. Or, if you prefer, 5.1 minutes. Now, just to make this into minutes and seconds, this 0.1 here, that's not representing like 10 seconds here or 1 second here, because the minute isn't out of 100 like the decimals are, it's out of 60. So 0.1 of 60 is going to be 6. Therefore, it's 5 minutes and 6 seconds for the time. What then is just our limitation of this model? Well, the limitation is that the equation doesn't work for any time after 5 minutes and 6 seconds, because that would then suggest that you could have a negative radius.